Welcome back to physical chemistry. Today we're going to look at infrared, which is the next energy state down. We're not going to go much further than this because then we get out of the range of chemistry. Infrared can be absorbed into oscillation of bonds in a variety of ways. So we can look first of all at the possibilities. This water molecule, for example, because it's bent, can do unfortunately everything. So let's start with something more simple. Let's start with triple bond carbon monoxide. That's not very neat. If we take a carbon monoxide molecule, it can't do very much. It can't bend because that would just be the same as rotating. It can't do anything apart from stretch effectively. So it's just stretching in this direction and compressing in this direction, or it's rotating. Oscillation of this bond can be excited by infrared, and that we can see if we measure it. But how are we going to measure that? For infrared, just like for ultraviolet and visible spectroscopy, we imagine a simple case. We've got a light source, we've got our molecule somehow trapped. So if it's in a liquid state, the carbon monoxide is typically a gas, so we'd need to contain it in a closed container. But if it was in a liquid state, we could have it in an open container. We can shine our light through our sample, and then it comes out and we need to be able to detect it. We haven't worried about those so far, so we'll have a separate thing about exactly how that's put together afterwards. But then we're going to detect it, so the simple school way to draw that would be an eye. Obviously it's not an eye because we can't see infrared radiation. This type of infrared radiation is typically far infrared. Near infrared is what is used by those heat detector cameras typically, and also the type of cameras where you can see in the dark. They use infrared lights. We don't want an LED for this because an LED shines mostly at one wavelength. We want some kind of equivalent of a light bulb, but it should be in infrared. And it's going to shine through our sample and be measured, and then we're going to have a subtraction type of spectrum. In our UV vis, we had our light coming in that was also from some kind of light source. We'll draw a bulb. Sometimes it is a bulb in those. Yeah, hope it doesn't look too rude. It goes through the sample, which is often in a cuvette in a plastic or quartz little square container, because we often look at liquids in UV vis. In infrared, it's not quite so easy because a lot of things absorb infrared light, so we are limited what materials we can use. But let's go to our detector. Our detector is going to also detect, and for UV vis, what we had was a scale in A, in absorbance, which is equal to the log of the intensity divided by the intensity if the sample wasn't there. We only do that because that is related to the concentration of the sample. Otherwise, there's no point doing that. That is a specific of types of visible spectroscopy or types of spectroscopy where the concentration can be measured. Infrared, it can also be used to measure concentration, but it's somewhat more difficult because the bond that is stretching and compressing, this C triple bond O bond, for example, varies somewhat. So if it's in a gas phase and it's a carbon monoxide molecule, it will have a certain absorbance intensity. But if it is connected to other things, then it will have a different intensity. For a lot of jobs that infrared is used for, we don't want to measure the concentration, and so we don't use an absorbance scale. It is used sometimes, but very often we use a transmission scale, which means that the graphs are usually measured in percent transmission, which is very unhelpful, wavelength on the other axis, and then we have peaks that go downwards, whereas absorbance peaks go upwards. So we already have a critical difference between the spectra, but it's just how they're drawn and not how they really are measured. if we go to our water molecule, we find there are a lot of things that it can do, partly because it's not straight. It's a bent molecule. So the bent molecule can be flexing, because it's got 3 bonds, it's got 2 bonds in it, it's got 3 atoms in it. So it can be flexing, which the carbon monoxide could not be. Carbon dioxide can flex, carbon monoxide can't, because it's got enough bonds to do that. But because it's got a bend in it already, the flex in one direction is not the same as the flex in the other direction, which would be sort of folding. There is also 2 types of stretching, one where one oxygen-hydrogen bond gets shorter and the other one gets longer, which is called the asymmetric stretch, so that it's really sort of cleaning its groin with a towel, effectively. The oxygen is cleaning itself, is drying itself off vigorously with a towel, and the other one would be stretching the exercise band, where both of them are going at the same time. So there are 2 possible modes of vibration where the bonds are being stretched. And of course the water molecule can rotate, but again, because it's not symmetrical, it has different axes of rotation that aren't the same. So if it rotates on this axis, it's not the same as if it rotates in this axis, and that's also not the same as if it rotates in this axis. This one I think was the one I missed out. There are 3 different axes of rotation, and they all are slightly different for water. What this means is that water has a lot of absorbances in infrared. The important thing about infrared spectroscopy is that we can use it to determine which functional groups there are in the molecules that we're looking at. So if we're trying to detect some unknown chemical that we've put in there, we would be able to see the carbonyl group, the C double bond O, and we would also be able to see whether it's got an OH group in it. That's because the oscillation, the vibration of the molecule, is determined by the strength of the bond and the mass of the elements on the ends. So a C double bond O is going to be defined by the mass of the carbon, the mass of the oxygen, and the strength of the double bond, which means that it will be different to a C single bond OH, which is a weaker bond because it's only a single bond, and it's slightly heavier because it's OH. The different bonds do interact with each other, and it does shift each other around a little bit, which makes it difficult to look at mixtures of different molecules. It's always a good idea to have your molecules, your test sample, as pure as possible for infrared. I said I was going to keep the mechanism for a different time, but I lied a little bit, because we need that just to explain why we do what we do. So because the infrared is going to be measuring bonds, then it will be difficult to use something with bonds in it as a container. So if we use a polymer as a container, which we would do for UV vis spectroscopy, because all we need is something that doesn't have too many double bonds in it, and even then what we really only need is something that doesn't have double bonds that are 1 bond apart from each other. So we've got a large range of possible materials there that are transparent in much of the visible region. But in infrared we don't have that. In infrared we will see polymers and we will see many inorganic species. What we would like here is something that doesn't have bonds in it, and the best thing for that would be an ionic substance. So we would like something that is ionic, something that is cheap and easy to use, and the most obvious candidate for that will be salt, sodium chloride. The problem with sodium chloride is it's a little bit brittle, and it dissolves in water that it can suck out of the air, so that's not very practical. But we can think of other salts that are similar, so we can think of potassium bromide. The potassium ion makes it more resistant to water. Sodium ions tend to draw water more in. So if you look at fireworks, they tend to be made more with the potassium salt of things than they are with the sodium salt. The sodium salt of firework chemicals are usually not as sought after as the potassium salts because they suck water out of the air, and then your storage is a problem. So we would prefer a potassium salt than a sodium salt, but sodium is usually cheaper. And there's a problem with making a big piece of sodium chloride, because we all know sodium chloride as little grains of salt that we might put on our food, but we don't know it as a sheet that you use to make things out of, or a cup. So that's awkward. What we can do is press it, and it will mold under high pressure, and then we can form little discs. So in the past, what people used to do was put their sample between two discs of sodium chloride or potassium bromide, typically potassium bromide. Then we can shine our infrared through it, and we can measure. That is another reason, that's why I'm saying this now, it's another reason why infrared is not often used for determining concentrations, because the practice of doing this is going to be problematic for concentration, because we're going to have to trap some between here. Because infrared is absorbed very strongly, we need a very, very tiny amount. We're talking about micrograms here between our two plates, and that will be obviously a bit of a problem. It's physically possible to do. People used to do it all the time. That's how I was taught. But there is an easier way, practically, that we use here. So what we use here is a crystal, no, not a crystal, a piece of material, let's call it that, which traps the infrared light. The infrared light comes in at an angle, bounces off the top, and goes back out again. So I've tried to organize that. I've tried to draw it so that this face is straight compared to the infrared beam coming in. It bounces at a low angle, and what we know from optical fiber technology is that if we bounce at a low angle on the inside of something with a high refractive index, like glass, then the light will tend to be trapped inside. It will tend to reflect off the inside face. What you might know from school is that there's something called the Brewster angle. So if we rotate this beam at some angle, the light will then be split into a reflected beam, which is coming back out, and a refracted beam which escapes. At the Brewster angle, the reflected beam travels along the surface of the sample. It effectively refracts down and down and down, and then because it would also be inside the sample, it doesn't exist anymore. If we get close to that angle, what it really means is that the light is getting very close to the surface. When it gets close to the surface, its field can interact with anything that is hanging around on the outside, which is confusing from a sort of understanding point of view, but it's very useful practically. Because if we take our sample and bring it and just hold it up against the surface, it has to be very close because it's inside the width of a light beam. It's inside the width of a photon, so it's a quarter of a wavelength approximately. It looks out a little bit, and it can be absorbed by something on the outside. That means if we bring our sample up and we put it on here, we can detect it without the light beam actually going into it at any point. It's weird and quantum mechanical, but it's very, very useful, because then we can keep this clean. For practical purposes, our one uses a diamond here. A diamond has carbon-carbon bonds only one type, because they're in a tetrahedral arrangement. They've only got 4 bonds. It's symmetrical. It's nice and pure. And the good thing about a diamond is it's chemically inert-ish. It's very difficult to break it with solvents anyway. We can heat it up to reasonable temperatures without anything happening. And it doesn't have infrared absorbance. Why doesn't it have infrared absorbance? There's a rule for infrared. So let's look at that. It has a selection rule. And the selection rule for infrared is a quantum mechanical selection rule that says if a transition involves a change in dipole moment, then it will be particularly effective in infrared. It will be selected for in infrared. The actual terminology is that it will be allowed, but quantum mechanically allowed is different to real allowed. In quantum mechanics, if you allow something, that means it happens a lot, and if it's not allowed, it means it doesn't happen very often. So it's not an exclusive selection rule, but things that have a vibration that changes the dipole moment are very, very strong infrared absorbers, and things that don't are very weak. And if we look at our diamond, there are only carbon atoms in there, so there is no dipole. And if we excite it, that means this average length of this bond will change, or the average angle of the bond will change, and neither of those things do anything because the carbon isn't polar anyway. So diamond is not very good at absorbing infrared. It's very poor indeed. If we look at our water, because the two bonds in there are polar and it's bent, nearly everything that we do to the water involves a change in dipole moment, and that is why water absorbs a lot in infrared. The unfortunate sort of exception to this would be our CH3 bonds, or our CH3 groups, which are not very polar at all. They're considered to be non-polar, but they're very slightly polarized, and they are reasonable at absorbing infrared. However, if we think of a typical organic molecule, there's a lot of carbon and hydrogen in there, and not very much of anything else. So if we think of pentanoic acid, and then we've got all of the carbons and all of the hydrogens. Every carbon's got at least one hydrogen. Most of them have got, most of them have got two, and some of them have got three. Let's change it to that. And the end carbon has got a C double bond O, OH, the acid group. The acid group is far, far more effective at absorbing infrared than the CH groups, even though there are a lot more of them. So the practicality of the ATR, which is this reflection method, or the problems with making plates out of potassium bromide, for example, means that even if we want to measure the concentration of something in infrared, it's kind of difficult because it's hard to get a known amount of it into the beam. Having said that, it can be done, but it's not done very often because it's tricky and there are problems. The main use of infrared is to identify organic compounds, particularly if we've purified them mostly from something. It's excellent for identifying polymers. It's used in waste recycling for identifying which polymer is in there. But it's also used for preparative organic chemistry if we're cooking chemicals and we want to know whether we did the thing that we intended to do. Then we take an infrared quickly to see whether that happens, because we typically will be changing one functional group to another. So that's fairly obvious. Then we can measure two things. We can measure, first of all, did the thing happen that we wanted to happen? And we can also measure how much approximately of the starting material is still in there, remembering that it's not very quantitative, that we can't measure things very well. Going back to that, we've got a little bit of a problem in German with, so German language, with the difference between quantitative and qualitative, because German has misuses the word qualitative for something else, but in science it has a meaning. It means you don't get a number. Infrared is typically used as a qualitative measurement, so you find out what is in there but not how much. Whereas UV-Vis is very, very often used as a quantitative measurement, meaning you find out how much is in there. Fluorescence, again, it can be either. We can measure whether something is in there. We can also measure how much of it is in there, but there's a problem with fluorescence because if the energy is passed to a different molecule, then we don't see it. It's lost somewhere else. So the medium that our fluorescent dye is in can change how brightly it fluoresces, so it is very difficult to use fluorescence as a quantitative measurement, but it is typically, it is more and more commonly used for that because it's a very useful technique. Infrared is, however, almost always used for identifying things. The unfortunate thing about infrared is that everything absorbs, and particularly water, and so that is why we go to Raman. Let's have a side-by-side look at infrared and Raman and use those funky diagrams. I'll draw those and then come back. So if we compare the techniques side by side, we're actually doing the same thing. We're starting off at the ground state of a vibrational energy state. So here is our energy well. We've got our energy well as an unbalanced U form, because that's very likely to be the case. On the short case, we can't compress it infinitely much, so there's obviously going to be a steeper and steeper barrier on this side, and on the long end it's going to open out somehow, because we're going to break the bond if we stretch it too far. So the same thing happens in total, in that we start off at the zero state, we go up to an excited state, or the first excited state, the second excited state, or the third excited state. In our Raman, I apologise to Indian people for pronouncing it badly, I should really ask somebody. We still do the same thing, however, we go from our ground state and we end up at the first excited state, the second excited state, or the third excited state, etc. The main interest here is that the result is the same, but what we do is different. So here we must put in different coloured photons, and they have to be the ones that fit the colour that can be absorbed, so the energy that can be absorbed. And we have to measure how much light we don't see. We're measuring all of the light that would otherwise go through, so we have to also send other photons of other colours through and measure them on the other side. With our Raman, we have a different problem. We send in a photon and we get out a photon of a different colour. If we need to measure that practically, then we need to have this one as a very well-known tight colour. So this one has to be a broad band light source, and this one has to be effectively a laser, a single colour light source. An LED would do it. So what we need is a very bright, very single colour source, but the actual colour doesn't matter as long as the wavelength, as long as the energy is way higher than the energy required to do the transition that we're going to have. So for Raman, we can use a visible light, we can use an ultraviolet light, we could use a near-infrared light. For practical purposes, and for us in biomaterials, we're interested in things that will go through tissue, so red is a particularly useful colour. Also, we would like to go through water, and so visible light is particularly useful for bio stuff. Obviously, it's reasonably simple to generate infrared photons. What we really need is something that's hot, and so we need a particularly rubbish old-style light bulb, effectively a bit of wire that current goes through that gets hot, but not hot enough to emit visible radiation. So a really, really rubbish light bulb, or what people sell as an infrared heater, so just a piece of resistor. Typically this would be a silicon bar, because they last a really, really long time, so you can afford to buy an expensive and nice one, and then nothing happens. It's not getting really very hot, so it's going to last a long time. It doesn't need a cover on it. In fact, it's better if it doesn't have a cover on it. And then we get a beam of infrared photons that we can send through our sample. For Raman, we obviously need a single colour, and we need a way to block that colour getting to the detector, because it's going to be very, very bright compared to the light that we actually want to measure, which is this photon here, which is shifted in wavelength slightly. So we would think, from looking at that, or from thinking about the advantages and disadvantages, why use infrared when Raman is so cool? First of all, we have a different selection rule. So the Raman spectrum will have different oscillations, different vibrations and bendings, so different stretching and bending modes that are active, because the Raman selection rule is that the polarization must change, so the gross size of the molecule must change, whereas the infrared is that the dipole moment must change. Some changes are both infrared and Raman active, some are neither, but many are one or the other. But a major driver is convenience and cost. So an infrared spectrometer is reasonably affordable. They are about the price of a car, and they are simple to use and fairly robust. A Raman spectrometer is also not super expensive, but some of the parts in it are expensive, so we need some kind of laser, and if the laser breaks, which they do, they wear out, we've got an expensive repair. Whereas in the infrared, there are not very many components that can break. There's this heater bulb element, which is very robust indeed, and there is another part that splits the light into different colors that we need to discuss at a different time. In the Raman, we've got to have an expensive type of filter to block the laser light from going into the detector, and we need a detector that can detect very, very small shifts in energy, which is typically also done using by splitting the light into different colors, but that needs to be far more accurate because we're using a small change to a big number rather than the absolute value, which is the case in the infrared. Also, most of the energy that we put into our sample in Raman is not doing anything. So pretty much 1 in a million of the photons actually turns into a Raman photon. All of the other ones are scattered and just go somewhere else and end up as heat. But also, even the Raman photons, many of them are not going in the direction that we want. And most of the energy in the light is in the light to start with, and it's in the light in the end. Whereas the infrared, if it's absorbed, it's all of the light goes into the vibration. What that means is that there is a high danger with Raman spectroscopy of cooking our sample, of putting too much energy in it. A typical Raman spectrometer will have millijoules of power, which doesn't sound like a lot, but if we see that they're focused to a tiny, tiny dot, then we have very quickly a problem. Even with ceramics, we can cause damage to them, and then we're measuring something, but it's not what we started with. Not that those things mean that Raman is completely useless, but it does mean that infrared still has a place in the useful analytical toolbox, because it is a tool that you can afford, that you can understand, that is easy to repair, and that is hard to measure crap with. Whereas a Raman spectrometer is comparatively easy to measure things that don't do you any good for a variety of reasons. My main focus with infrared, however, is more about the practical use of it, because we don't have an infrared course in organic chemistry. And therefore, we're going to look at the bonds that we would measure in infrared. So here we have a list or a table of infrared absorption wavelengths. Starting at the top, we can see OH from alcohols. There are 2 versions, as you can see, and one of them is medium and sharp, so it's not very big but very narrow, and one of them is strong and broad, so it's comparatively big but it's also very broad. And you can see that it says on one of them that intermolecularly bonded and the other one says free. What that means is that our alcohol group, when it's free, is not attached to anything, and when it's intermolecularly bonded, it's attached to something else, probably by hydrogen bonding. So if we have our alcohol in water, it will be intermolecularly bonded to water, and so we'll see a strong and broad band. And if it is dry and two alcohols can't get close enough together to each other to bond, then it would be free. So typically, if we have a surface with alcohols on it, they will be free alcohols. and if we have a very dilute solution of alcohol, it will appear to be free alcohol. But if we have a strong solution or a strong liquid, or we have something else in there that can hydrogen bond, we will see the broader signal. That again goes to the problem that we have with infrared, that the strength of the absorption and also the breadth of the absorption depends on what the bond is otherwise doing, because we can imagine the strength between an oxygen and carbon in an alcohol, the bond, the strength between the bond in an oxygen and carbon in an alcohol will vary whether the lone pair is doing something or not, and whether the hydrogen is hydrogen bonded to something else or not. Likewise, primary amines, so that's the next one down, also is affected by hydrogen bonding. So NH stretching and NH stretching, it varies too. What did I want to say here? Yes. You will notice that we're using a scale for our x-axis here. So although the y-axis is percent absorption, which is comparatively simple to understand, the x-axis is now in per centimeter, which is the 1 over the wavelength. So it's effectively wave number. It's 1 over the wavelength, which means that we've got a reciprocal, which means that it's not the same distance between points. They get further and further apart, or closer and closer together, depending on which way we look at it. And that is deliberate because a wave number scale is linear in energy, whereas a wavelength scale is not. So it makes the scale better for infrared, and it's the traditional way to do it. Also traditionally in infrared, so if you look at the scale, it will usually be backwards. So this 3700, which is the longest wave number, the shortest wavelength that you use, is typically on the left at the beginning of the scale, and it goes down to the right, but also because it's a reciprocal scale. So the wavelength is getting bigger. But what else do we have here? We have other OH stretches from acids and from intramolecularly bonded alcohols. So that would be the ones that are bonded to other things. Intra to itself. So if it's bonded around in a circle to something. And what do we have below that? Then eventually we come to CH stretches in alkynes, alkenes, and alkanes. So the carbon-hydrogen region effectively is down between 3,300 and 2,800 something. These are shifted slightly depending on what they are, and the interesting ones are, or the ones that we always see, almost always see, are the CH stretches at on CH2s and CH3s, which are at around 2,900 to 3,000. There are 4 of those. That's because there are different stretching modes. So we've got umbrella, where they go like this, because there's 3 of them. And we've got scissoring, which is the equivalent with 2. Then we have stretching and asymmetric and symmetrical stretch. But what we actually see as strong absorptions is 4 bands, and 2 of them actually overlap, so it looks like 3 usually, but it's actually 4. If we have a molecule that only has CH3s in it, like tertiary butyl something, then we will obviously only see 2 of those. And if we have molecules that only have CH2s in, which is fairly common in rings, because then there isn't an end, or in really, really long hydrocarbon chains, then there's comparatively little CH3s compared to CH2s. In those cases, then we only see 2 peaks, or we see 2 big ones and tiny ones. That usually tells us some information. It's hard to directly interpret it, but very often we've got an idea of what we've got, because we know what we started with, if we're doing preparative chemistry, or if we're doing a problem or measuring something, we have some other measurement. So typically, in traditional organic chemistry, we would know the elemental composition of the compound. So we'd know its how many carbons, how many hydrogens, how many oxygens, how many nitrogens are in there, and we just don't know what order they're in, and the infrared tells us, there's an alcohol, so that's what one of the oxygens is doing at least. And otherwise we would actually be cooking, so we would have a good idea, either we've made this or made something accidentally, but we know what the conditions are and what the chemicals are that we deliberately put in, so we can guess what it would be, which cuts it down a little bit. Scrolling down the table a little bit, we can see other useful peaks, such as the OCO stretch on carbon dioxide, which you wouldn't think we would need to know about, because what's carbon dioxide going to do there? The problem is that the carbon-oxygen bond is extremely, extremely good at absorbing infrared. That's why carbon dioxide is a good greenhouse gas, but it's also why carbonyl groups, for example, of all kinds, are really, really easy to detect in infrared. The problem in infrared is that there's very often some carbon dioxide in the air in the spectrometer, or in the air outside the spectrometer, depending on the setup. And that means that we will often see this peak either positive or negative, depending on whether our reference sample, when we tested the beam, whether that had more carbon dioxide in or less carbon dioxide in than when we do our measurement. So we can see this peak upside down very often. It's good to know where that is. It's also helpful to check that our spectrometer is doing what it's supposed to be doing, because it should always be in the same place. If we do want to measure something that's in the same place as carbon dioxide, we obviously have to be careful about keeping the atmosphere constant. If we use an attenuated total reflection, an ATR, like the one we have, like the one I explained to you just before, it's all sealed. So it's comparatively easy to keep the atmosphere constant. And what that means is we can get rid of the carbon dioxide peak almost entirely. But in an old style infrared, it wasn't possible. In really expensive infrared machines, the whole of the optics is under vacuum, and we don't have that problem either. But yeah, we have to pay money for that. And obviously, one of the main interests, the main important features of infrared spectroscopy is that it's comparatively cheap, and as soon as you have a vacuum, then you're throwing that advantage away. What you can see also is that there are a whole lot of other possible functional groups in this region, but they're comparatively weird ones. So things like isocyanate, which is superglue, but also carbodiamide and things like that, which they're comparatively uncommon, and if they're in there, we would expect to suspect that they're in there beforehand, that there's a reason for them to be there. Triple bond as well. You don't usually accidentally have a triple bond in something. Moving on to the next region, which is to the right, but it's lower in wave number. We get to the C double bond O's, and there are a lot of these. Obviously, it's near to the carbon dioxide peak, but not super near, because the next carbon also affects the electrons. The other oxygen from the carbon dioxide is also pulling electrons away, so it affects the strength of the other one. And in this case, we've got a little bit of a gap, so it's relatively easy to see that this isn't carbon dioxide, but then we get all of the possible carbonyl groups, so not only acids, but also acid anhydrides, where we've dried them, esters, what else we got? Lactones, which is a ketone, aldehydes as well, so all possible variants, and they're all shifted slightly compared to each other, but a lot of them overlap, so it's very difficult to tell exactly which one you have unless you've got a reasonable idea, or unless you have a really well resolved spectrum. Sometimes they come out very sharp. Very often the peaks are kind of rounded and difficult to tell. But this is one peak which you should probably always look for, because if it's not there, it also tells you something useful. Below that, there's all kinds of unsaturation, which means double bonds. So there are all kinds of other transitions that we can see due to double bonds being in our molecule, so C double bond C and C and other things. Those are also really useful because it's otherwise quite hard to find a double bond. The problem being that if we know how many hydrogens are in our molecule, we could have a ring, we could have a double bond. Infrared is a good way of telling. There is a problem because if we go further down the table, we run into a region where there is a lot of stuff, where a lot of possible things happen at the same time, and a lot of the backbone of the molecule can have absorbances, and they move around quite a lot, so it's comparatively difficult to analyze. So first of all, do the ones that are easier. But we'll go down to the next step on the table. So now we have bending of CH bonds. We had the stretching and the umbrelling beforehand, so this is a different type of movement of the carbon-hydrogen bonds, and we can also see these. Obviously, very often there are a lot of these, but it can be useful. As we go further along, we'll see there are lots and lots more things. So here we can see there's a lot of overlap between these absorbances, so if we didn't know which one it was, we would struggle with just infrared to tell the difference. If we know that there's an oxygen in our molecule and we know other things from the spectrum, then we can usually make a decision, but it can be challenging. As we go further and further down, we'll run into problems, but most spectrometers don't measure below 400 or 800 wave numbers, because there will be some kind of window in there, either a window to the detector or a crystal for the ATR, or a beam splitter or something, some kind of coating inside the machine, and depending on what those coatings are made from, they will block the infrared at some point. And typical known values are 400 and 800 wave numbers. Very often it's not very useful to measure below 800 unless we're looking for inorganic compounds, because there are just too many things that are similar. So we'll stop here. So this is what we would expect to see as an example problem that we may maybe get for organic spectroscopy in infrared. We will not add too many other types of spectroscopy to this, because the next one would usually be, for a chemist, would usually be NMR, and we probably won't manage that. We'll have a go at it this time, but it's a different type of spectroscopy and it works in a completely different way. Let's have a look at this. So we've got a possibility, so we know effectively that there's carbon and oxygen, just one oxygen in our molecule. We know about how much carbon, we know about how much hydrogen, so we've got these potential structures, A to E. Oh, you can see my, I'm not sure whether you can see my mouse. Oh, that's weird. It's got a shadow. Yeah, that's weird. Anyway, going down to the spectrum and starting from the left, from the high end. So let's first of all check where our carbon-hydrogen peak is. So this is our carbon-hydrogen peak. There are others, obviously, but this is the one that we're interested in right now. That's going to give us a reference for where the other ones are. Above it, we would expect to see OH if we're going to. And we can see this lovely broad peak here. It's very big and it's broad, which tells us that it is it's hydrogen bonding to something. So we've got OH in our molecule. That tells us that A is not right. B is also not right, C is probably also not right, so it's one of D or E. Can we work out anything else from this? Well, we've got a shape here that looks like not too many peaks, which, as I was telling you before, is a clue, because if we have CH2s and CH3s in our molecule, we would expect to see 3 or 4 peaks here, and that doesn't look like it normally looks. Unfortunately, from our D and here, we have little choice, because we've got this one which only has CH2s in it, and this one which has 2 CH3s in it and 1 CH2. Oh, it has 2 CH2s. So it probably is E from that. That's giving us a suspicion. Let's have a look at the other things. So if we look down here, we would expect to see somewhere here a giant peak for C double bond O if there was any, and it would be really, really huge. So it probably isn't. And that would pretty much do for this molecule. Let's have a look at the answer. So this is the answer to the problem in text. You can see that I missed that they gave you the chemical formula and I didn't get the number of hydrogens. So there's obviously a double bond or a ring in the molecule from the number of hydrogens and oxygens, and that tells us that it can't be the second last one, so it was the one that I said, but we can also tell that from the carbon-hydrogen bonds, as I pointed out. So this is question 2. I can't see the, oh yeah, here's the chemical formula, so that's what they used to get a clue, but let's do it without that clue to start with. If we look from the back again, we can identify our carbon and hydrogens, and we can see that there are more clearly 3 peaks here than there was in the other one, and there's a little leg here which would give us our 4 peaks, which is good. That's indicative, well, it's not good, but it's indicative of a normal chain. Out here there is this tiny peak which might be something, but it's probably not. This isn't big enough to be an OH because they usually get on that. It's probably a little bit of water in the sample. If we go down, we can see there's nothing for a while, and that's very common in infrared spectra. As you noticed in the table, in this region there were a lot of fairly esoteric groups that we are not going to encounter that often. Then we see this massive sharp peak, which is obviously something important, and if we count down from 20, 19, 18, it's at 1700 and something, so that is clearly a C double bond O peak. Looking through here, we've got that, which it can't because it's not got an OH. This, it can't be because it hasn't got a C double bond O, it's got an oxygen in the middle. This one it could be, but it isn't because there's got too many peaks. It's got 3 or 4, and that would only have 2 because it's only got one type of carbon with hydrogens on it, these CH2 here, so it can't be, it can make 4 peaks here. 4 peaks here. So this one is the one that I'm looking at now. Then it could be this one. It can't be this one because it's got OH at the end, although it's got this funky ring on it. So it should be D. Let's have a look at the answer. I have to flip window and flip. Okay, so they've done much the same. They've said there must be a double bond or a ring in the molecule. Because there isn't an OH peak, we can rule out A and E. But we do see one at 1700, which is CO, so we can safely rule out B, which gives us D. Because they say the 2 oxygens, okay, it doesn't match the number, but also it's the CH. So I think this is the last one. Now we've got what looks like a complete disaster out here in the long wavelength region. The CHs just poke out here. So we've got some CHs. That's good. It helps us to identify our spectrum, and we've got a broad OH on top of it, which is shifted somewhat, because for an alcohol it would be slightly further out here. Let's leave that for a little bit, or keep it in the back of our head. We see it. So we know there's an OH in there, and continue. See what else we have. So there's nothing in here, and then there's this massive peak again at, it's over 1700, but it's not 1800, it's 1750 or something like that. That's our typical C double bond O, so it's a carbonyl group. With a carbonyl group and an OH group, that sounds very much like an acid, which would be B. It could also be D. Having a carbonyl group and an acid, having a carbonyl group and an OH group, the shift of the OH into here is what we would expect if they're connected together, because effectively this double bond O is extracting electron density from the OH, and so that's going to move its frequency somewhat. And if you look at the table, you can see that acids are shifted over here and alcohols are shifted over here. So that's what we would expect to see, and we can identify it fairly easily. It's not a very difficult molecule to identify otherwise because it's very smelly, but that is, so the only one that would cause us real trouble here is D, because we might get confused by that one. All of the others are easy to knock out. This one here with its little ring, what I did check was whether there's any unsaturation there, whether there's too few hydrogens in there from the chemical formula, which they expect to do. It's just their style of question. So here is their answer. They use the formula again to more effect than I did. They also use what they call airy beard, so that wide knobbly bit. It's a big peak with lots of little peaks on top of it. That is typical for carboxylic acids, but also the shift of the OH into the CH region really is typical. Of course, you wouldn't remember that in an exam, but with a table, you would see that it has a different frequency to the OH frequency, so you would be able to deduce that. I don't expect you to remember everything, but I would like you to be able to do these, because we've got to start somewhere.